Well, hello everybody. It is time for a video about what we can do with the mean and the standard deviation of a data set. So far, we have learned to take some raw data, measurements, whatever they are, raw data, and calculate the mean and also calculate the standard deviation. But I haven't said much about what that tells us or why we would do it or anything of that nature, okay? So this video is about those things, the mean and the standard deviation, and some predictions that we can make about the data and the data set, okay? Well, what's the stat cat have to say? First, we better learn about a concept. Standard deviations from the mean, okay? What does it mean to say the data is so many standard deviations away from the mean or something like that? Well, so let's think of it like this. We have a kind of a general expectation that in most situations we would expect most of the data to be near the mean or near the average. Like whatever the average is, most of the data is going to be close to that. But, you know, the word near, notice how I underline that. That's not a very mathematical word. You know, like, it's kind of like this. Like, the word heavy is not very mathematical. But the word 200 pounds, or the number 200 pounds, is mathematical, okay? So, we need some way to put a number on that. Or we think, yeah, most of the numbers are going to be near the average, but what do we mean by near? Okay, so I took some sample, like this would be like kind of typical grades on an assignment. Okay, so I can tell you from years of experience, like it wouldn't be strange at all if I had 5 students take an assignment that maybe something like this would happen. Okay, so there are 5 grades. All right. And I wanted to calculate the mean and the standard deviation for that sample. Okay, so here are my calculations. The mean is 70 and the standard deviation is 31.1. Okay, so the mean is 70 points on the assignment and the standard deviation is 31.1 points. Now, real quick, here are those formulas for the mean and the standard deviation. Okay, to find the sample mean, you add all the data values together and you divide by how many data values there are. Okay, this symbol right here means you add the results together. All right, so that says add all the data values together and divide by the number that there are. And then the standard deviation, oh, I forgot something. It's the square root of that. You take each individual data value, you subtract the mean, and you square that number, and you add all those results together. And then you divide by one number less than the number of data values there are. And then the last step, take the square root of that, and that's the sample standard deviation. Okay, so that's how I calculated both of these things by hand. Now, we are going to talk about this concept of what does standard deviations away from the mean look like, or what do we mean by that? Okay, so here goes. I put this all on a chart because I kind of assume most people are visual. Okay, so like here's the whole spectrum of grades, we'll say. All right, and real quick, I noticed I put one of the numbers in the wrong spot. Hold on just a second. That's more like it. Okay. So here's the whole spectrum of grades, and there's the mean grade, okay, 70. And then like these 5 dots represent the other scores. So we had a 79, we had an 80, we had an 85, we had a 91, and then we had this really unusual score of 15, like pretty far away from the others. Now, to look at this in picture form, the mean is 70. And the standard deviation being 31 looks like this. To be one standard deviation away from the mean would to be up here at 101.1. I took 70 plus 31.1. I get 101.1. And to be one standard deviation less than the mean would put me at 38.9. Okay? I take 70 and I subtract 31.1. So to be one standard deviation away from the mean, in this case, puts you somewhere between a score of 38.9 and 101.1. Okay? And yeah, it looks like you see all of the scores except one were within one standard deviation of the mean. Two standard deviations from the mean, that would be even wider, right? I'd have to take 70 and subtract 2 times 31.1. That would put me down here at a score of 7.8, okay? And if I took 70 and I added 30, like 2 times 31.1, that would put me off the chart, all right? But that's what I'm saying when I talk about standard deviations from the mean. You calculate the mean, and you can jump one standard deviation above or one below or two above or two below and so on. Now that's how we'll talk about things, okay? When we talk about this right here, when we have this like instinct that, you know, most of the data is near the mean, we're gonna quantify that in terms of numbers by talking about how many standard deviations from the mean is the data. And this is how we're going to say it, okay? Data entries that are more than 2 standard deviations from the mean are generally considered unusual, okay? And data entries that are more than 3 standard deviations from the mean are very unusual, all right? And I mean that standard deviations away from the mean or the average, you know, like this. You can jump 1 standard deviation, 2 standard, and so on, okay? So that's how we can think about whether a number is unusual, okay, in terms of how many standard deviations away from the mean it is. Okay, so now that kind of gets us started on this. We've got to take it a little further, though, okay? Now, next concept is if a data set is bell-shaped, okay? Another word for that is normal. So if a data set is known to be bell-shaped or normal, we can use something called the empirical rule to make some predictions about the data. Now, how about this? Before I tell you what the empirical rule is and what it tells us, let me tell you what I mean by bell-shaped. Do you remember the frequency histogram? That's something that we learned about at one point, okay? You could take a data set and you could present it graphically in a frequency histogram, all right? This is what a frequency histogram looks like when we had learned it. If the data was bell-shaped, like, you know, like this, bell-shaped, then the frequency histogram would look like this. It would be, you know, symmetric, like here's the middle, and then the right side and the left side look about the same. And it kind of resembles like a bell if you could trace over it, see? So that's what we mean by bell-shaped data. All right, it's not all clumped together on one end or the other end, or it's not evenly spread out. It looks like when you see this frequency histogram that most of the data is in the middle and not so much of it is far away from the middle, okay? Now, the reason it gets its name being bell-shaped is if we had a very large data set, then this picture would tend to smooth out into this one, okay? Where most of the data is in fact in the middle, not very much of it is far away from the middle on either side, all right? So the mean is right in the middle. And we'll find that about 68% of the data, if the data is known to be bell-shaped, okay, if it has a frequency histogram like this, which tends to smooth out into this picture if there's lots of data, then 68% of it is going to be either within 1 standard deviation above the mean, or the mean's right in the middle, or 1 standard deviation below the mean. Okay, so that's what happens with bell-shaped data. So if you're doing, you know, anything with statistics and you're told or you see that the data is bell-shaped, then, you know, that's what you can expect. Now, here are the predictions by the empirical rule for bell-shaped data. First thing, calculate the mean, the sample mean and standard deviation if it's not already given. And then here are the predictions. Okay, about 68% of the data will be within one standard deviation of the mean. Within one above or one below the mean. And 95% of the data will be within two standard deviations of the mean. And virtually all of the data, 99%, will be within three standard deviations of the mean. Okay, so it's like, only 1% of the data is going to be more than three standard deviations away from the mean, all right? So those are the predictions by the empirical rule. Remember, the empirical rule is for data that's bell-shaped. Let's do a question, all right? So here's like kind of a typical sort of example that I can show you to illustrate this. So let's say that we know this data is bell-shaped, okay? And we do some study, maybe we survey people or something like that, and we find out that based on the survey and the answers that we were giving, or however we found this information out, the mean monthly utility bill is $70 per month, okay? And that with the data, we did all the math, and we found the standard deviation is $8 a month, okay? Well, all right, then here's the prediction we can make. What happens if you take 70 and you take away 8? That would give you 62, right? And what happens if you take 70 and you add 8? That will give you 78. Now, between $62 a month and $78 a month, that would be within one standard deviation of the mean. And so I can say 68% of the households in the study are going to have a monthly bill somewhere between $62 and $78 per month, right? Because that's what it says. 68% of the data will be within one standard deviation of the mean. Mean 70, standard deviation's 8. That puts me between 62 and 78. Take it a little bit further. 90. How do I get this claim? See this claim right here? This prediction? 99% of the data are between $46 a month and $94 per month. Virtually everybody in the study has a monthly utility bill between $46 and $94 per month. Where did I get those numbers? Well, see the 99% right there. The prediction is 99% will be within three standard deviations of the mean. So if I take the mean of 70 and I subtract 8 three times, that would be three standard deviations below the mean. And if I take 70 and I add 8 three times, then I would get $94. I get three standard deviations above the mean. Okay, so that's where 99% of the data would have to be. Okay, so that's the kind of prediction that we can make. Now, this is what you see here is called the empirical rule, and it's for bell-shaped data. Not all data is bell-shaped. So, we might wonder, is there a similar sort of prediction that we can make? The empirical rule is for data that is bell-shaped, and that's it. Not all data is bell-shaped. You could kind of imagine with all the frequency histograms we ever made or that you ever saw when we were learning about this, they didn't all look like this. Okay? So they can look kind of level, they can look kind of heavy on one side, light on the, they don't all look like this. Okay. So not all data is bell-shaped. We can make similar predictions for other kinds of data. It's just any kind of data, all right? So this is called Chebychev's theorem, and it says the portion of any data set within k standard deviations of the mean is at least 1 minus 1 over k squared. And that's for k being 2 or more, okay? Well, let's do the math on this and see what it says. So what if k was 2? What if I wanted to say the portion of any data set within 2 standard deviations of the mean? Okay, well, if k is 2, then this 1 minus 1 over k squared is 1 minus 1 over 2 squared. And if you calculate that, you do the math, you get 3/4. On your calculator, you may get 0.75, okay? But that translates to 75%. So for any data set, we can say this, at least 75% of the data is going to fall within 2 standard deviations of the mean, okay? All right. At least. maybe more. It says at least there, maybe more, but at least 75% of the data is going to be within 2 standard deviations of the mean. And say, what if k was 3? Okay, why not? We got this formula. So that would be 3 standard deviations of the mean. That's, according to this, 1 minus 1 over 3 squared. You'll get 8 over 9. Or, depending on how your calculator's set up, you might get 0.888, so on. And so that, in terms of a percentage, would be, with some rounding, 89%. Okay, so here's how we translate that. 89% of the data are within 3 standard deviations of the mean. At least 89% of the data are within 3 standard deviations of the mean, maybe more. Okay, so that's Chebychev's theorem. Now, let's see an example of that. I mean, we got these statements, but let's see one where we'd have to take that as knowledge and apply it to some broader situation. So here we go. Let's look at this one. Say that we do a study or a survey, whatever, of 20 households. And we ask everybody, well, how many TVs do you own? And we record all the data and so on. Okay, so let's say we find from that study of 20 households that the mean number of televisions per household is 3. Okay, so it's like saying the average number of televisions per household is 3. And then we have a standard deviation of 1 television. Okay, all right. Now, question is, can we use Chebychev's theorem to determine at least how many of the households have between 1 and 5 televisions? So if there's 20 households in the study, the mean is 3, the standard deviation is 1. Well, how many of the households have between 1 and 5? Now, let's map this out a little bit. Here's how I see the information. Now, if you're solving this problem, it's not like you have to write down this elaborate flowchart like me, but this is an instructional video, so that's what I'm doing. Okay, so this is kind of how I imagine it. So imagine here's a sort of a graph of televisions per household, and the mean's right there at 3, and the standard deviation is 1. So to have between 1 and 5 televisions, well, 5 would be 2 standard deviations above the mean, and 1 would be 2 standard deviations below the mean, right? Because the standard deviation is 1. Here's the mean, 1 standard deviation, 2 standard deviations. Okay, and then here's the mean, 1 standard deviation, 2 standard deviations. All right, so that would be 2 standard deviations. So we could translate this to saying something like, how many of the households are going to be between 2 standard deviations of the mean, either above or below. Okay, so let's think of it like this. What portion is within 2 standard deviations of the mean? Didn't we just figure that out? If k is 2, we use that formula, and it says something like, it says 75% of the data is within 2 standard deviations of the mean. Okay, now that's the portion. 75% is the portion. All right, it doesn't tell me how many. I don't know, I could say I have a class of 30 people and 50% of my students are male. What does that mean? How many students are male then? 15, right? So 50% is the portion, and then 15 is the number. All right, so I know that 75% of the data is going to be between 1 and 5. But how many is that? How many households in the study are within 2 standard deviations of the mean? 75% doesn't tell me how many. There are 20 households in the study, okay? So the number of households that are within 2 standard deviations of the mean is 75% of 20, whatever that is. The way you calculate 75% of 20 is you multiply 0.75 times 20, and you get 15 households, all right? So the ultimate answer, how many households have between 1 and 5 televisions? Well, since there are 20 in the study, 15 of them have between 1 and 5. All right. Now, but it's all based on this statement right here of Chebychev's theorem. Okay, that 75% of the data is going to be within 2 standard deviations of the mean. 75% of 20 in this case. Now, real quick, about percent calculations, because we may have to do some percent calculations at times. And, you know, when we say something like 75%, okay, that's how we talk about it. Those are, that's the word, 75%. We don't do the math with 7.5 like that. The way we do the math is with 0.75. So the way we talk about percents is not the same way that we do the math with them. So notice, here I said 75%, but my math was 0.75 times 20, all right? Okay, so there are lots of little details like this that might come up in the class that seem kind of buried in the overall picture. So if anything like that comes up, you can let me know. But otherwise, we'll end this video with Chebychev's theorem, just like you've seen it.